every time you go live.
You go live? Go live?
Try to do that.
Yeah. But the user is asking you to make this kind of like streams say, hey, you are online already.
Okay, good.
So this is automatically on. How come it can be automatically on?
Because you gave the key, and he entered the key.
Okay, but how come, so could I edit this one? So lecture number, this is, I guess that this is number 7 or something. Lecture 7. Yeah, that's okay.
But I can sit, Aki, maybe that's even
You
better.
can, I mean, you want to sit?
I think that's even better if we
No, I
do.
think it because I,
We
Let's
can
see.
we can fix the green screen. No?
yeah, we can fix it.
Wherever you want, just let
And
me know.
then
You wanna
take a
sit?
look.
No,
I can
it's
shift
okay. So,
Because I see how it is here.
okay.
So trust that we can do this looking good. So you just, now is Anand is located in the lower, no, it's actually the entire bottom of the slide. So maybe as soon as you want to make it this in lower left corner perhaps,
Sure.
but it's really good quality. Looking
Thank you.
good. Except that there is something that is coming off on that right side. Can you crop?
Yeah. I'm doing that.
Yeah. That's a good
But
sign. And then you just
this
stop there whenever
is-
it's not so well visible. Yeah, like this. Look at that. Have you never been in this high quality stream?
Oh man, I should
And the headset. You need to put the headset on.
Yeah. Oh, headset.
Is it okay?
So audio. First, we have to get the audio here, right?
Hey.
Yeah.
What is it? Jabra link.
Yes.
Okay.
And then
Right.
this one. It's kind of funny that you need to wear this headset, but otherwise, online participants they don't hear you.
Okay. And then I have to make the sound audio input here. Jabra, right? Well, now we should have sound. Now we should have sound.
No, still no.
No?
Let me see. It might be because of my settings too.
Jabra, okay. Jabra. Yeah?
Is this the way that I should hear?
Yeah.
I mean, this way that I should hear.
No.
Not this
No.
way. Okay, hold on. So it was my mistake. So I'm
Yeah.
going to take a look at the stream itself
Yes.
because I'm in a studio, YouTube studio.
Yes.
Okay, so it's clear. Loud and clear. Loud
Okay.
and clear.
I'll keep it like this, otherwise I have no connection with others. Let me listen.
I think it needs using.
Yeah.
Okay.
Just one thing.
But I think that there's too many audio inputs, so that's
Yeah.
Yeah, we can do
You
that.
can mute some of them.
Wait. Which one is this
Uh,
one? This is the audio capture.
Yes,
right?
the capture.
So let
That one. Yes. Now it should work. Now you should have one audio. Now you should have one audio. Now you should have one audio. Okay, great. Yeah. You can guess about the disappointment. Yeah. So funny to hear yourself in a delay, in a serious delay. Yeah, sure. Come on. So I have to point. No, but I cannot point there. Sorry? Yeah. Yeah. Yeah, but if I point in that direction, how does that look? That looks. Yeah, I'm going to use my mouse. I'm going to use my mouse because that will otherwise look very strange, right? Yeah, that's good. That's good. I have to do it anyway to flip from the screen. So, Suraj, this is not here. This is not here. For me, this is not here, right? Hmm. Well, to be honest, if I look at the clock at Loot, yes, I should have a talk to the dean. So this doesn't work, right? Somewhere. The quest is which one is it, right? Yeah. Yeah, that's good. I can do 45. No, no worries. Yeah. What's this? That's a chocolate effect. Yeah. Well, then you're disappointed because he's not going to talk. Yes. Nine 11. Yeah, correct. No, I was going to Ithaca at Cornell. Yeah. Yep. Yep. Engineers. Thank you, Aki, for the kind introduction. So, my name is Arend Schwab. I'm an emeritus of Delft, and I'm now here as a visiting professor at Lutz for a number of years. I'm very happy to be here. Usually, I come around to summertime, but this time I told my wife, let's go in a winter month because I love winters, and it's really good. I enjoy. So, I'm going to talk about bicycle dynamics and control. Maybe the subtitle is The Art and Science of Cycling. And then you're going to think, why am I going to talk about art? Well, I think cycling is kind of an art. How you learn to cycle, I will address that point. So I will address two things. First of all, the bicycle in itself as a mechanical system. And then secondly, which is far more important actually, what is the rider doing on the bike? Um, the motto is actually that everyone knows how a bicycle is constructed, right? It's two wheels and a steering assembly, and it's not so complex. Also for an engineer, most of us we can tinker on our own bike. We understand how it works, but yet the operation of cycling, and mainly not propelling, but the operation of keeping balance and steering and maneuvering. Um, Most people have an idea what they do, and I like to dispel that in this lecture and show that you actually have no clue what you're doing on the bike from a sense of balancing and maneuvering. I could not have done this work by myself. I mean, that is the beauty also of academia, that you are able to collaborate. Open science, you can connect to peers and friends and other universities. You meet them during an internship or either a sabbatical or whatever. You bond, like I bonded to Aki, and then you do collaborative work. This was done together at TU Delft, of course, my alma mater, where I have most of the collaborators, but then also at Cornell University, where I did a sabbatical year. That was at the time of 9/11, by the way. And then at UC Davis, which was also rather bike friendly in the US. There are two key publications on this, and I think the first one is in the Proceedings of the Royal Society. That is the journal in which Isaac Newton already published. So we are among good friends, I would say. And that was a building block for the second publication. So the first is just on the linearized equations of motion, a benchmark paper. And then the second one was building on that. That is in science, like what makes a bike self-stable? Why can a bike stay upright by itself given some forward speed? And there was a lot of myth and folklore in the literature, so there was room for clearing that up. And that actually started the whole bicycle research also at Delft. So some observations. So here you see a movie by Jacques Tati, a very old movie. I'm old, so I show old movies. And this is a 1949. It's about a postman who wants to rationalize his work. And in doing that, he's going to use a bicycle to go faster. And you see a bicycle move by itself, and everybody said, yeah, well, this is a movie, right? Everything is a trick in a movie, so this must be a trick. But actually, it's not a trick. Any bicycle can do that. And if you notice, it even goes around the corner by itself. If there's a little bit canting on the road, it can do that. So bicycles can do that. It's not a trick. You take a random bike, you give it some speed at an open space, and it stays upright given that speed. Whereas if the bike is at zero speed, it falls over, right? So in some way, this forward speed gives it its stability, I think. Well, I say it's not only stable, it's super stable because you can propel it, you can hit it sideways, it starts oscillating, and the oscillation dies out. And we as engineers then say, oh, a dying oscillation, so there must be damping or somewhere in the system, right? It's a nice damped oscillating system. So next question is, of course, how does it come that the bicycle behaves like that? Well, the history of the bike is very old. If we go back to the first contraption, that was Carl von Drais, 18 something, 1820 or whatever. And so he made it a thing which he called a hobby horse, because people used to ride horses, but then this is a horse, well, something which is not alive, but you can still propel yourself. And it's a hobby, sort of, maybe. It was a way to go faster from A to B without having a horse. Well, to have a hobby horse then. How does it work? Well, you have two wheels, a steering assembly, and you propel yourself with your feet on the ground. You pedal, you touch the ground, and by that way you move forward. And then the next step in this evolution is actually that they mount pedals on the front wheel. So you don't have to put all the time your feet on the ground, but you can move the crank of the front wheel with your feet, and then you can propel yourself. Now, there is in the human genes, there's some gene, and I don't know which one it is, but there's a gene which tells you faster. Somewhere, everybody has this gene. It says faster. Whatever you do, you want to go faster. So also in cycling, you want to go faster. Well, there's an easy way. If you want to go faster with the pedaling this front, you just enlarge the front wheel, right? I mean, for every revolution, the amount of distance you travel is larger. So if you do that in the same time, you go faster. But, and then you see that at the left bottom here, there is some constraint. You cannot make the wheel infinitely large. And the constraint has something to do with human, your legs have a finite length. So that's it. And then you see a nice jump, and that's why I call it evolution. You see a jump. Suddenly they say, oh, I can do a chain drive, and I can drive my rear wheel instead of having these pedals on the front wheel. But it is a jump. It's a jump in evolution because the bike still has this large front wheel. And that clearly shows, it's evolution, right? We change step by step small things, and then again, somebody said, well, you don't need a big front wheel. You can also have a small one, just to demonstrate very small. And then finally, we get to a contraption here, which is 1890 or something like that. And that's the bike you see out there. Every bike looks a bit like this bike. Yes, question. I love questions. Yes. Well, what is your question? Then you go faster. In people, in our body, we can use our muscles at a certain speed. If you exceed a certain speed, you cannot exert force very well. As an example, in speed skating, ideally you would push backwards, but I mean you have to push so fast backwards with your muscles, you cannot do that. So therefore, we push sideways in skating. So there is this human problem about the speed by muscle so we can contract. So therefore, the only way to do is keep that same cadence in pedaling and enlarge the wheel. Yep. Okay, so around that time, 1890, also scientists wondered about this bike. So, and they noticed that the bike can be self-stable already, like this machine. And of course, they wanted to know, how does that work? And like in a lot of things with science, it happens at two spots at the same time. Leibniz and Newton were both working on this differential calculus. In this case, Whipple from the UK and Carvalho from France were both simultaneously, but independently of each other, working on this stability of the bicycle. And they made a model. A very simple model, of course, as simple as possible, but not too simple. So there are a lot of assumptions. Rigid rider, fixed rigid rider on the frame, hands-free operation, everything is symmetric. Knife edge wheel, so there's point contact. There's no side slip. There's no friction or propulsion. You're not going up or down. And then, if you think of this system, these two wheels and the steering assembly, under these assumptions, you end up with a system which has 3 degrees of freedom. Meaning that if you take a bike, you can say, oh, I can move forward, the bike can lean, and I can operate the steering assembly. So those are the 3 degrees of freedom you have in the system. Note, by the way, that under all these assumptions, this model is energy conservative. So if we think of the video we saw, where we hit the bicycle, it oscillates and the oscillation dies out, that sort of contradicts the idea that we have here a model which is energy conservative. So maybe that model even cannot predict this dying oscillation. So let's see. The model in itself has 3 degrees of freedom, leaning, steering, and forward motion. However, the bike itself has like 27 parameters, like the wheelbase and the mass of every of these 4 parts. You have 4 parts, 2 wheels, 2 frames, rear frame, front frame, mass, inertia, wheelbase, head angle, trail. So a whole list of those things. So meaning that the family of bicycles is large. We have all kind of different bicycles which we can make, right? And it's interesting to see that all bikes almost look alike. Anyway, we want to study the stability of the forward motion. So what we do, we just take Newtonian mechanics to derive for this multi-degree of freedom model the linearized equations of motion. So we start from nonlinear, then we take the nonlinear equation, and they have the form of mass times acceleration, the first part, and the rest is forces on the right-hand side. But in the linearized form, we push it to the left-hand side to get this differential equation. So this is inertia, actually. This is gyroscopic type of forces, and this is gravity and something to do with when you go in circles that you have centrifugal forces. That is in a nutshell the equations, but on a higher level you see we have 3 degrees of freedom, but these are decoupled, these equations. So the lateral motion, being the leaning and the steering, is decoupled from the forward motion. And to the first order we see that to the first order, the linearized equations tell us, oh, the forward motion is constant. If there's no propulsion or no resistance or whatever, so forward speed is constant. And then the other 2 equations, they all have to do with the lateral dynamics of the bike. So the coupled leaning and steering. And we see from the equation, and we see also from the numbers in these matrices, that there is a strong coupling between leaning and steering in the bike. And even if you take a stationary bike and you lean it, you see that there happens something with the steering assembly, right? Or in other ways, if you have to constrain the steering assembly with the torque to keep that 0 steering angle. So there is coupling going on at 0 speed, but also at non-zero speed. Well, if we focus on 0 speed, then this cancels out, and we have mass and gravity. Just the normal thing which we are used to with a 2 degree of freedom system. But then when speed comes into play, we have this very strange, cranky, linear, sort of pseudo-damping gyroscopic thing. And if you look at the entries, it's strange. There are zeros. It's not really skew symmetric, so there is some damping going on, but there was no damping in my system, right? So that's strange. Then the gravity is just inverted pendulum at a high number, and then this gyroscopic term only works, of course, on the steering. Only at the steering, finite steering angle, you have these gyroscopic terms. You have these centrifugal terms. Anyway, you can ponder on all these numbers, etc., but you want to investigate the stability. So what do? You assume exponential motions, which you substitute in the equation. Then you get this characteristic equation. We have two second-order differential equations, so we get a fourth-order characteristic equation. And this fourth-order characteristic equation we can then solve, and then we get the 4 eigenvalues of the system. I find speed very interesting because the stability at 0 speed is very bad, whereas at some speed there's stability. So I want to see how the eigenvalues develop as a function of forward speed. So here I make a plot. At the horizontal axis I have the forward speed, and at the vertical axis I have the eigenvalues I have from the eigenmotions. And if there's a blue line, it means it's the real part of the eigenvalue, and if there's a red line, it means that's the oscillating part. So initially at 0 speed, we are here. Then we see 4 eigenvalues, AB and minus AB, and that is just like a double pendulum. And it's an inverted pendulum, so it's very unstable. So we have like 2 eigenvalues with 2 modes of this double pendulum thing. You can compare it to that. But then, when speed increases, we see that 2 of these real eigenvalues come together and they form this conjugated pair, or they form an oscillation. So an oscillation is going on, but it's still unstable. And then when speed goes on, the real value becomes 0, and apparently this oscillation, which is initially unstable, becomes stable. So already this very simple model predicts that the thing can be stable from a certain speed on. Of course, there are other modes going on. So this is an oscillatory mode. This is a capsize mode, which is stable, and then at very high speed becomes mildly unstable. The real part is small, so it takes a lot of time for perturbations to double. So that's not so important. Why do we call it capsize? The bike slowly falls over in itself without much steering, but very slow. So that's an instability which is not so important. And then this is a very stable mode, we call it caster, that has to do with the front wheel. If there's a non-zero angle and you move forward, it wants to align immediately. And that's a very stable thing. Okay, so let's look at these modes, and let's first take the unstable ones. So the bike, you propel the bike, and it starts oscillating, and the oscillation grows and it just falls down. Actually, this is what happens when you learn to ride a bike. You don't know how it works, you go slow, it isn't self-stable, you have to do things, you have no clue what you have to do, and you crash, right? So most of the time when you learn how to ride a bike, there's a helper, either a parent or a friend, and he just pushes you, right? Because we have this feeling already that if the bike has some forward speed, it's a lot easier to balance. Or he grabs you by the neck and it just keeps you pushing forward. But there is this solution, of course, and that is more speed. So in this, you see a simulation where we have higher forward speed, self-stable. We hit it sideways, it oscillates, and the oscillation dies out. Exactly as we saw in the experiment in the open road. So yes, this model predicts that a bike can be self-stable from a certain speed on. Remains, of course, for you the question like, a damped oscillation and there is no damping going on? So there's no energy lost? How can that be? Question. Okay, self-stability. Let's look at that. How does that work? Well, to try and understand how a bike can stay upright by itself, that is a very hard question. Actually, I have no clue. But maybe we can compare it to balancing a stick, because that's approximately the same thing. Now I make it even simpler, the bike. The bike has only 1 degree of freedom, leaning. And how do I balance a stick on my hand? How do I do this? Yeah, by moving the support. So very easy. So if the stick falls to the right, I move my hand to the right. If the stick falls to the left, I move my hand to the left. Every time I try to get this support point underneath the center of mass. And by that way, I can balance. Well, a bike is a little bit like that, right? But to do that, then I have to move Earth. Yeah, I mean, yeah. Maybe we should talk a little bit more about it after the lecture. Yes, maybe. But however, there's other solution. You have a steering assembly, and on a stationary bike, nothing much is happening with the contact points. But on a moving bike, if you steer to the left, your contact points go to the left. And if you steer to the right, your contact points go to the right. So on a moving bike, you have an apparatus by which you can move your contact points. And now comes the magic of the whole thing. So if you fall over to the left, what do? You steer to the left to get upright again. And that is a very counterintuitive thing. So initially, when you mount a bike and you start riding and you feel you're falling over, you steer in that direction. It's even getting worse, right? So, and that's what I mean. It's also an acquired skill how to learn how to ride a bike, and that's an interesting thing. Anyway, this is how to balance. As a proof of principle, we have students also at Delft who do projects. Here they did projects in a robotics lab with the Lego Mindstorm. So you have Legos, motors, sensors, and a computer. And then you can make mechatronical things which move around. Usually they made a walking robot. This guy, he was into motorcycles and he said, I'm going to build a motorcycle because I have motors, I have sensors, wheels, Legos. So he built a motorcycle out of this. There are two motors in the thing. Of course, there's a steering motor here. There's a propulsion motor. There's a sensor here, which senses the thing is falling over. And there's a computer here. And then, well, he was an avid motorcycle rider, so he knew how he rides motorcycle, how he balances and control. So he wrote a whole control program based on the sensorial input of the lean sensor and the forward speed and the steer angle, and the thing crashed all the time. Whatever program he made about balancing, the thing crashed. So apparently he had no real idea about how do we balance a motorcycle. Although he's an avid motorcycle rider, he can do it. He cannot write it down. So what to do? Well, he went to the lab and to my lab, and somebody said, "Yeah, Schwab there in the back. He has a bike lab, and he knows about bikes. Maybe he can help you." So, well, to balance, you have to steer into the fall. So there's an undesired fall to the left. You have to steer to the left. If you go to the right, you have to steer to the right. That's the only algorithm you have to apply. And how do you do that in your machine? Well, you have a sensor. You have a lean rate sensor. So you take the lean rate and then you have a motor on the steering. So that's probably a DC motor. So the amount of voltage you put on it is the amount of torque. So why not put the voltage on the steering motor proportional to the lean rate of the bike? And so it can be -8 or +8 or -80 or +80, but that should be the control law. And then it was quiet. Joep looked me in the eyes. I said, "Yeah, okay, Joep, what's the problem?" He said, "Well, it's only one line of code in my controller." I said, "Yeah, okay." Joep went away, and I think 5 minutes later he came back with this video. And I think this is the living proof that you have to steer into the direction of the undesired fall to balance. Right? That's how you balance a bike. And we see that also if we look at, coming back to you in a sec, if we see that in our video, slow motion, we see it's falling and then steering. You see it's falling and then steering. So a bike can do that by itself, by steering into the undesired fall. Question? I'll get to that. We're not talking about maneuvering. We're talking only about the bike now. I'll get back to that. Yeah. Okay. So this is about what we observed. The big question is, of course, where is the intelligence of the bike? So how does it know that it has to steer into that direction of the fall. Does it have a fall sensor, or is there some bright computer going on? Well, actually, there are two teams, two explanations, and it's like in politics: if you have the left wings and the right wing, or you have the snitches and the creatures, or you have a La Paranta and Tampere team of hockey. I don't know. There's always two, right? And one team, they say that's obvious. It's the gyroscopic effect of the front wheel. I mean, you have this wheel which rotates, and it's like a gyroscope. So this is the front wheel, rotates in this direction, meaning you have an angular momentum vector like this. And then if then on a second axis the wheel is tilted, then on the third axis you get a torque. It's like 1, 2, 3. It's a real three-dimensional thing. And then if you check, if you take a wheel, propel it, and then tilt it, oh yeah, you feel the torque. Oh yeah, okay, that's it, done. No. Then the other team says, absolutely not. It's about the steering assembly, about the geometry. If we look at the geometry, we see that the steer axis is tilted and that the contact point is behind the steering axis. So if we look at the picture, we see this is the steer axis, hits the ground here, but the contact point is here. So it's a distance behind that, like in a caster wheel. On a shopping cart or whatever, you have these caster wheels, contact point is always behind the steering axis. And that makes that if the bike tilts, it steers in that direction. And yes, if you take a stationary bike and you do that, that's what happens, right? Okay. So let's go to team number one. Well, team number one is about these half gods who live up there somewhere, the untouchables, right? It's Felix Klein and Arnold Sommerfeld. Arnold Sommerfeld was nominated 81 times for the Nobel Prize. I mean, I'm still waiting for the letter. 81 times. Felix Klein from the Klein bottle. And among the work they did was also a lot on gyroscopes, and they wrote a 4-volume books on Die Theorie des Kreisels, or the theory of gyroscopes. On your shelf, it will be something like this. And then the 4th volume was this nice thick book with all kind of examples. And of course, everywhere where they looked, they saw gyroscope. A gyroscope. A gyroscope. Everywhere are gyroscopes. And they looked at the bike and said, oh yeah, there's a gyroscope, so that must be it. And then together with Fritz Noether, they derived equation of motion. Of course, they knew their classics. They knew the work by Whipple and Carvalho. They said, here we will demonstrate that what Whipple and Carvalho showed in their analysis, that the gyroscopic effect is the one and only factor which makes the bike self-stable. So it's a necessary condition for self-stability that you have this gyroscopic effect. This is from their book. Yes. You have to look it up. Yeah, directly from the book. They really like the gyroscope, yes. And then they say, yeah, well, the stability we found, according to Whipple, is just because of gyroscope. If we kill gyroscope, it doesn't work. However, if you check the derivation, there are two tiny sign errors, two errors, two small sign errors, whatever. But if you fix that, it's not so obvious that if you kill the gyroscopic effect, that the thing cannot be self-stable. Other things are in play then too. So this is a sort of a debunk of the gyroscopic effect. I mean, it can help, but it's not a necessary condition. You can probably make bikes which are self-stable without gyroscopes, right? Yes. That's absolutely. Yes. Even half god. Absolutely. Absolutely. Because the problem in this whole bicycle dynamic self-stability world was Every time after 1910, that was when the series was published, the books, every time after 1910, when people talked about self-stability, they said, oh yeah, it's a gyroscopic effect. Klein and Sommerfeld showed that in their book. And then everybody said, oh yes, yes, of course, Klein and Sommerfeld showed that in their book. So you have to be critical, even if it's Klein and Sommerfeld, or even if it's Akimikola. Be critical. Yeah. Okay, so fixing those sign errors is not clear. Yeah. Yeah, it is. Then you're a hero, right? Okay. Then, so Camp Gyro lost, right? So apparently then the other are the winners, right? So the geometry. So this is about David Jones, who published in the 70s a paper. And on the stability of the bike, he was more interested in why are bikes so easy to control given some forward speed. And he related that to that self-stability of the bike, of course. Well, he again knew his classics, so he knew Klein and Sommerfeld, but he was skeptic about that. He built a bike where he killed the gyroscopic effect by mounting a counter-rotating wheel to the front wheel. And then if two of these angular momentum are in the same frame, then they cancel each other out. And then he said, "Whoa, mommy, I can even ride without hands." I mean, what gyroscopic effect? Debunked. It's not important. I can control the thing, no problem. But then he tinkered with this steering assembly thing. Where is the contact point? He either made it very large behind the steering axis, or he made the contact point in front of the steering axis. And then he said, well, if it's in front of the steering axis, it's very hard to ride the bike. I cannot ride without hands. So it must be something to do with that. So he went into an analysis with potential energy to show that the trail is here dominant, and if you need to have positive trail in order to be self-stable. Now, unfortunately, potential energy is the same in a moving bike as in a stationary bike. So the analysis missed some terms, and if we add the dynamic terms to the system, it's not so clear that you need a finite trail, a positive trail, to be self-stable. Another example. So again, but then remains the question, of course, what makes the thing then self-stable? If it's not gyro, if it's not trail, what else? What else does it? Well, it's easy, right? Because we have the equations. We have a model of the bike, so we can form the equations of motion. We can form the characteristic equation, and we can apply the Routh-Hurwitz criteria, meaning we get 6 criteria, which all have to be larger than 0. And with all these inequalities, we can stitch and find out which parameters are important. However, you have 27 parameters, right? If you symbolically crank this out, I can paint at least and print out the result. I can paint at least all the walls of this university with the result. And that is not the final result. Those are the inequalities, which I then have to follow and stitch one into the other. So it's an unsolvable problem for us. With so many parameters. So what we do, we make a very simple bike. So we cancel out the gyroscopic effect. So we make it on skates. I mean, in the Netherlands, we're good speed skaters, so we make it on skates. No rotating wheels. And next, we make a contact point which is exactly on the steering axis. So there is no trail. Contact point is directly on the steering axis. That force is applied there exactly on that line. And then we take a very simple mass distribution, just 2-point masses. And then we get a system where we only have 8 non-zero parameters. And now it's doable to write down about this stability criteria. And then we can find contraptions of this machine without gyro and without trail, which people thought was necessary for self-stability, which is still self-stable. As you can see in the graph, we see from a certain speed on, this contraption shows self-stability without gyro and trail. Now, it could be, of course, that this is just about very small numbers. So we build it in a multi-body system software. We give it finite disturbances, and yeah, it stays upright. It oscillates a bit and it stays upright. So that's promising. So let's build the machine and see if we can really make such a thing. So, of course, on skates is doable. You can go to a skate hall, but we put just a counter-rotating wheel on top of the front of these wheels to get rid of it, and we made the trail a little bit negative, a little bit in front of the contact of the axis, because in reality you always have a finite contact region. And then the net lateral force, if you have a finite contact region, can be behind like the centroid of that contact region. So to be dead sure that that lateral force is in the elastic or friction type of way, is really on or a little bit in front of the steering axis, we put that little negative trail there. Then you build the machine, you go to the hallway of the sports hallway, you propel it, you bring it up to speed, and you release it, fingers crossed, and stays upright. Without gyro, without trail. You do the same thing, you propel it, you hit it sideways, it starts oscillating, but it stays upright. And that was exactly the topic of our paper in Science. So a bicycle can be self-stable without gyro and without trail. Showing that these two myths, which was always going on, you don't need that, other factors. And of course, people ask, why does it stay upright? Yes, self. Yes, exactly. Yeah, exactly, exactly. Yeah, you just have to find the right topic. This contraption from a certain speed on is self-stable. To first get in the self-stable region, then it's easier to control. Correct, yes. So the big question is, of course, if it's not gyro and not trail, then what is it which makes the thing self-stable, right? Because we are always looking for this holy grail. What does it make self-stable? And our message is actually, in a normal bike, it's a mixture of things. I mean, gyro can help, trail can help, but in this case, it's the mass distribution which makes the thing self-stable. And bear with me, so if this is the contraption, so this is the mass of the rear frame and this is the mass of the front frame. If the thing is falling over, then this mass being in front of this axis will make the steering turn into the fall. So if it falls over, because it's that unstable configuration, the steering will also, and just due to the mass distribution in this case. And as you have seen here, the conditions about self-stability are the mass in this region, the mass is unconditional. You can have any mass as long as it's in this region. If you put the front mass in this region, it's conditional. There's some equation, but meaning it has to be somewhere in front, conditional, either unconditional, but it's mass distributed. And that means that you can make, if we connect self-stability to ease of control, which is also a question, but I think it's probably right. If you connect it, you say a bicycle which is self-stable is also rather easy to control, and you want an easy to control bike, then you have all kind of ways to do that. I mean, the bike as we see it now outdoors is not the only solution. There are all kind of other ways. Unfortunately, you see in practice, like for instance, let's take a folding bike. In a folding bike, you have very small size wheels. However, the whole steering assembly is sort of copied with a head angle and the trail from a regular bike. And meaning that the control of a folding bike is always a very nervous thing. And then people say, oh yeah, that's clear because of the small size wheels. And then we say, need not be. You can change geometry-wise things or mass distribution things such that you have approximately the same type of control on a folding bike than on a regular bike. Until yet, nobody has done it yet, unfortunately. But those are a lot of options, and we use this theory to make bikes for elite racers handle better. We use it for low racers, which have adjustments to have it the same sort of handling at different forward speeds. So it is theory which we really can use. Okay, we addressed only a very small topic now because we only talked about yes question. On a real bike, yeah. So then you have to think, okay, I have a steering assembly, meaning that I have a stem and I have a front fork and a front wheel and I have handlebars. And for that whole assembly, there is some center of mass. And that is what the MH sort of stands for. Where is that center of mass? So you're not always free to do that. But on the other hand, you are free to change head angles for the steering assembly. You have a lot of freedom. Yes. Yeah. 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 And for instance, there are in the Netherlands, it was very in vogue for high school students who have this basket on front of their bike. And the basket is not connected to the rear frame, but to the front frame, meaning it moves with that handlebars. Meaning that you put the center of mass a lot forward. If you put your backpack there, and I don't know if I noticed, at least in the Netherlands, because a lot of those bikes were there, that they really swerve on the bike path, meaning that there's a control issue there probably going on, right? Yeah. Okay. So that is, we touched already control issue. So the bike itself is interesting, but far more interesting is what are we doing on the bike? Yeah? How do we control the bike? Well, propelling is sort of easy. You just put your feet on the pedal, you pedal like hell. But with the steering assembly, how does that work? Here you see a picture. Two people. One is very famous, and that's my daughter, of course. I used her to study how do you learn to ride a bike, and on the other hand, some other guy. So the big question is, how do we control that? And if you observe, you say, well, I steer, I move my upper body, and so there are all kind of ideas about how you balance a bike, right? So maybe you can think for yourself, how do you balance a bike? What do you do? Any idea what do you do to balance a bike? Your bike? And what do you do when you ride without hands? And what do you do then? Yeah, okay. So so some people say you tilt your upper body. Other people maybe ride with hands, maybe smart. I don't know. So okay. Mm, yeah, you can see. Okay, so we okay at Delft we had the same. Like, how do you control the bike? And there was so many ideas about how it's going on. So we said, this is room for science, right? So here we have to investigate. So what do we do? Well, first of all, you have to ask yourself the question: when I maneuver a bike, what do I do? So very simple. If you want to go to the right, if you want to go to the right with your bike, what do you do? Yeah, okay. In which direction do you steer? Right, okay, right. Yeah, well, you go to the right, right? And lean, what do you do with your upper body? Something? I love this answer. I'm not sure what I do. Lean, you lean to the lean or steer? Counter steering. Okay. Anyway, what do? Well, it turns out that you very briefly steer to the left and then to the right. And with your upper body, you just go with the flow. You do almost nothing. So why do you steer to the left? Well, to stay into a turn to the right, you have to lean into the corner, right? How do you lean in the corner? The moment you start moving your upper body one direction, the bike moves the other direction. I mean, nothing is happening. What I'm doing here, nothing. I cannot exert a torque against the outer world. I can exert a little bit lateral forces by doing this, but not so much. So leaning doesn't make me lean as a system, but by steering, I can control my leaning like hell. So if you steer a little bit to the left, bang, the bike immediately falls to the right. And then if you let go of the handlebars, you're in the corner to the right. And here you see that video also going on. So a little bit steering to the left and then bang, immediately you fall. And I really encourage you to do the experiment to cycle with not by holding the handlebars with your fixed hands, but with your open hands. And then push a little bit with your right hand. And then you feel how quickly the bike will fall over to the right. And then how much the steering assembly wants to go to the right the moment the bike is leaning. So that is this nice coupling, lean to steer. That's the beauty. So if you want to dispel this, say, no way, I can go to the right without steering to the left. I can do that. I just use my upper body or whatever, or my brains, or I do it. Well, try and do it in the snow, because then you have a clear proof of what you are doing. And you can do it as many times as you want, but you will also see these two paths cross. You will always see you have to first steer into the undesired direction to get the thing leaning. That has to do because you have to lean into the curve to stay into the curve. Otherwise, you will be thrown out. And you will be thrown out because while you're in that curve, there's nothing you can do. You cannot do like this to start leaning. It doesn't help. Yeah, a friend. Or throw away your bag. Yes. Yes. Yeah, I know the videos. Yeah, they're cool. They're very cool. And another thing is maybe if you're not really conscious about this, you know that if you cycle very close to a curb, right? You for some reason know that it's a very dangerous situation. Unconsciously. So unconsciously, you know that to get away from the curb, you have to steer first into the direction of that curb. Otherwise, hey, you have to steer a little bit to the right and then you can go left. Otherwise, you cannot go left. Well, there is this very quick trick which you may do, which mountain biker people do, by swifting a quick swift of their body. They can, in a very transient way, get a small change. And then you can sort of escape a little bit this very narrow thing. But for a regular cyclist, as we are, not too close to the curb, please. Yeah. Okay. So we also wanted to know, how does that work? First, of course, instead of starting with the experiments, what do? Literature research. Yes, always. That's the way to go, right? You not start by inventing the wheel yourself, but say, hey, did somebody already invent the wheel? So in this case, two, and there are two studies. Actually, one is coincidentally from Delft, also in the 1970s, on this this human control on the bike. Now, why was this study done? There was, as you see, it's not a real bike; it's a bike simulator, simulating a bicycle. With hydraulics and electronics and a very ancient PDP-11 computer and so on. So what was the purpose of this study? Well, not so much as to observe how people are riding a bike, but to address the question from the Ministry of Transport. Is it dangerous to ride a bicycle if you are intoxicated by alcohol or drugs? It's a very legitimate question, right? For some reason, people who are intoxicated tend to use the bicycle, right? Some people think it's not dangerous. Other people think it's dangerous. So there's so statistically, it's exactly, yeah, yeah, you're totally right. Still, the Ministry of Transport has doubts. So, well, they had to come with: is it allowed to ride a bicycle intoxicated? Yes or no? So for cars, it was clear. For bicycles, not so. They started this study, and well, believe it or not, they needed volunteers, of course, for it. And the whole hallway was filled with volunteers because there was free drinking of alcohol and free smoking of pot, and then riding this contraption. The outcome was also pretty obvious. This was a control group who did it, so they fitted a rider control system on that. The outcome was if you are intoxicated by alcohol or drugs, then your feedback gain will increase enormously, making the thing rather unstable. Plus, your dead time, hey, your delay time will increase incredibly, which also makes the system very unstable. And then they wrote to the Minister of Transport, well, it's probably not a good idea to have people intoxicated on the bike. Yes, it is. It is. Yeah. It's good to know. No, longer. Oh, I'm falling over. What should I do? Let me think. I followed a lecture by this Dutch guy. Uh, Pull to the left, steer. What was it, left or right? Oh, you're already there. Yeah, yeah. Then on the other side of the ocean in the US, some research was started on motorcycle dynamics and control by David Weir. And that was mainly because the DOT, Department of Transport, was asking the questions, seeing the statistics that relatively there were far more accidents with motorcycles than with cars. Even if you correct for exposure, etc. And then the question was, is this a dangerous vehicle? Should we ban that from the road? That's how the Americans are. Oh, dangerous vehicle, not allowed, period. But so they had to substantiate that choice, and then they asked the researchers, can you investigate this rider and control thing on motorcycles? And that work continued on, actually. There was also a nice story about a rear wheel steered motorcycle. The idea was, oh, front wheel steering is probably very dangerous. Maybe you need rear wheel steering. That's a lot more safer. Well, actually, a rear wheel steered motorcycle is very safe because nobody can ride it. It's impossible to ride. But anyway, so motorcycle. Yes, exactly. Yeah, statistically. Okay, so back to the bicycle. So there was little after the 70s, little known about riding control, and we wanted to know what makes a nice bike, and what are handling qualities, etc. Um, so we did a bike with instrumented it with all kind of sensors and also a camera mounted on the rear frame, looking at the rider, so you see the relative motions of the rider with respect to the rear frame, and then just a simple ride into town with all kind of obstacles and things. So this was my PhD student then working on that. And of course, it's nice doing outdoor because you have all kind of things, but you get also a lot of disturbances going on. And if you then later look at the data set, you see all kind of things going on, and then somebody has to look at the video. Oh yeah, there was a dog, or oh yeah, there was somebody come from the right. So I mean that doesn't work so well. So what did we do? We went to a laboratory environment, to a very large treadmill in Free University of Amsterdam. It's a beast. It can go fast. You can tilt the platform. People used to do inline skating on this, but you can also cycle on a treadmill, of course. And if you take a bike and you ride with a constant speed in the constant direction or forward on a treadmill, constant speed, that is totally equivalent to riding with constant speed on the open road. It's a Galileo invariant, and so that's good. You can do that dynamically. It's the same. So knowing that, you just say, okay, how does it feel? How to ride a treadmill? Well, that's me on a bike, and of course I'm old and stupid, but I sort of can ride a bike, right? But I cannot ride a treadmill, a bike on a treadmill. So what was going on? The problem is on a treadmill, you have not all the correct sensorial information. So you are pedaling, but you're not moving because your environment is standing still. So your whole brain get totally freezed in all kind of ways. Like I'm moving, I'm not moving, and then you start doing crazy things. Usually you stiffen up, and that's not good, of course. And there's a trick. Either you look into infinity, you just start cycling and you look into infinity, don't look too much at your surrounding, or you look at your front wheel. Okay, you start pedaling and you just look at the front wheel because that is really moving. So after doing a short course on how to ride it, you can then do these experiments and do the observations. You measure with sensors what's going on. And oh, this is a safety line, by the way, which you see. And then you just, at the video, look at it. And then at various forward speeds, so at high speed, mid speed, and low speed. And actually, if we looked at the video first, we were totally surprised to see this guy at low speed that we thought you do your upper body motions, but it looks that the guy is really sitting like this with respect to the frame, very stiffened up. But I can tell you he wasn't. He was just balancing and controlling. And you see his legs are moving a little bit in and out relative to the frame, but for the rest, the upper body is staying in that plane. So we had an idea that most of the control is actually done by steering. So what we did next, we really went to an experiment where we measured everything. So with motion capture, we measured the motion of the rider and of the bike. And then with principal component analysis, we reduced that. And then we came to the following conclusion, that if you then start from the main motions to the minor motions, then the main motion is, of course, the bike itself. And you see very nicely here the coupling from lean and steer. So lean and steer is coupled. That's one of the first motions. Then the second one is that you change a little bit as a whole system the direction. Thirdly, of course, pedaling is going on. And then some bending of the spine, but it has nothing to do with balancing. It has to do with that you have to pedal, and then therefore you have to, oops. No, I started my dismiss. Come on. Why is it not stopping? Help. Yes. So that has to do with the pedaling. Then a little bit upper body sway is going on, and that is this one. Then, of course, the steering, and then knees up and down in a double frequency, and that has to do, you pedal, you push down twice in one cycle. And then finally you see knee motions, only knee motions going on. And then when you have all these components from large to small and you plot them as a function of forward speed, you see that the knee motion is dominant at very low speed. So that's together with steering. And then at higher speed that goes away, and then mainly the steering is going on. So why did we do this? We wanted to know from a control perspective, what type of system is this? Is this a MIMO, multi-input, multi-output, or a SIMO, single input, multi-output? And clearly, for balancing, it's a single input system, steering, period. And that makes it a lot easier to identify rider control systems. I thought that I was in business. The moment we had a publication with a Proceedings of the Royal Society, and then a couple of years later with Science, I thought every grant application we write, we just get the money, no problem. We, yeah, first I was waiting for somebody to come to my office. That didn't happen. Yeah, yeah. Coming with money. No. But so we wrote grant proposal, and every time the grant proposal was cancelled. And we thought, what the heck is going on? I mean, we are doing good science. And every time the main commentary was, yeah, bicycles is old, what's new, what's interesting? I mean, they are around, they work, so what is the problem? And then suddenly the light went on in our head. We said, what is the relevance to society? And to our luck, people were still dying on their bike. And more people were dying on their bike. So if you then looked at the statistics of the accidents in traffic with cars, they are going down. I mean, Mission Zero, what the European Committee said, that is working. We have less and less death in traffic with cars, less and less seriously injured. If you look at bicycles, that is going up. Every year we get more deaths in traffic and we get more seriously injured. And seriously injured on a bike, usually they are elderly, means within 3 years mortality. So you could say the seriously injured among the elderly are also sort of death in traffic. So what is going on? And of course the answer was, oh yeah, it's all these electric bikes, all these elderly people on the electric bikes. That's far too dangerous. They go too fast. They cannot operate the machine. And now we came into play as scientists by saying either partly dispelling that, saying, no, that's not really the problem. We did research on that, but also working on solutions for the elderly. Can we make a bike which helps them to balance and control better? And those are a number of projects. When that started, also the other part suddenly started, the sports engineering part that was established at Delft some 15 years ago now, I think. And then from sports engineering, they heard, oh, bicycles. Actually, we are an elite team and we have some problems in our elite team in cycling, either with the bike or with the riders or with the Olympic teams. We want a new bicycle for the track cycling. Can you help us? And so suddenly also all the things in the sports application with cycling arose. So it's two tracks actually, consumer and sports. So on the one hand, it was on the left, it was about elderly on a bicycle. So elderly, normal bicycles, e-bikes, compare what are they doing, do they still have attention, etc. So it was dispelled that the e-bike plays a dominant role in that. Actually, it's very good for elderly to have an e-bike because then they keep with the same speed as the rest of the cyclists. Whereas if they have a normal bike, they go a bit too slow, and that creates conflicts in traffic. So actually, an advice is to have elderly on an e-bike, but with a learning curve. And then on the right-hand side, we started with an elite team. This was about optimal power production in a time trial for an individual. How should you distribute your power during the time trial? Yes. Yes. We're doing great work, right? Yes. And and a beauty of these sports. I initially I never thought I would be have any contribution in sports, but in the end we worked among things for the Olympic track cycling team and the Dutch team. I don't know if you know it, but they won a lot of gold medals on our new bike, and of course the bike probably has played a role in that too. But the beauty of the thing is that now as a scientist, I feel I see these gold medals and I think, wow, because a gold medal, you cannot buy a gold medal. Well, you can buy it, but you can only win a gold medal. And winning something that's magic. And the same with these elite teams, with the Tour de France teams, and when they then win a Giro, wow! So that is an extra thing which you can have as a sports engineer. Aki? Yeah. Whole new experience. Yeah. Yes, please. Yeah. Yes. Exactly, and also at the equipment. So a lot of attention in the past in sports has been given to the biomedical thing, by the person itself. And of course, that's the motor that has to do the work. So that is important. However, if you look at the cyclist, for instance, the bike is like part of the system, right? It's an elongation of yourself. So if you make that very optimal, then probably you will perform very well. And as an example, again, this track cycling team, when we looked at it, they say, why do you want a new bike? They said, well, because we want a new bike, and that was it. Yeah, what is the problem? And then, yeah, well, no, we actually want a new bike. And of course, no, we as engineers think are problem solvers. We think, what is the problem? What do we have to solve, right? So, but then if we did an observation study and we did a lot of interviews and so on, we noticed all bikes are too small. The riders do not fit the bike. Some were hitting with their elbow, their knees, etc. So we propose to have that fit in a better way, but still have the same handling and dynamics as their old bike, as an example. So that was a sport. The other one for the consumer market, this is a steer assist bike. So instead of saying the rider has to balance, you can put a motor and a sensor on it, which then auto balances this bike or helps the rider because it applies a torque. You can override it if you want to, but it helps in balancing the bike. So there was a project which finally it's becoming some sort of product. The other one, we want to do experiments in a safe way, and you cannot go, you get no ethical improvement if you do some experiment on the outside with people and you say, oh yeah, they can fall or trip or whatever. No can do. So we build all kind of bicycle simulators. The one on the right, which you see, is what I call the bike simulator with the bucket, because this bike is not leaning yet, and you get confused with the head mount display and not leaning, and some people get very nauseous. So then we move on. Then we make a bicycle simulator. This was for a sports application where we just move the contact points. Like as I explained, well, how does balancing work? Well, move the contact points. In this way, we have two linear motors, and we have built a bike among those two contact points. And then we use the kinematics of leaning and steering to move these contact points, just kinematic motion. And the dynamics, well, that's done in the real world by the guy sitting on the bike, pedaling and leaning and doing whatever. Of course, you have to make sure that he doesn't run off the whole thing. So there's a slow controller, put him in the middle. But this feels like just regular biking. Then a question from the University of Groningen was elderly starting and stopping with their bike. They have trouble with that. So can you make a simulator where you can mount a bike, start pedaling, stop and dismount? And so we built this machine, which has actually the roll axis is just below the ground. And then you can steer and you can pedal. So the 3 degrees of freedom. There is actuation going on. So the whole roll motion is actuated. You don't see it. It's behind in these two bags and a belt going down. So we can actuate the roll motion. So we can make the bike either very stable or very unstable, depending on what we want. And more on that, we have also a motor for the steering below here, which gives you that feedback torque on the handlebars, which you feel like while you're cycling. And of course, we have a motor for the resistance for the pedaling, and then some visual display. Well, this is an initial thing. You see a screen here, but it will be a bigger screen or multi screens. We're not happy about head mount display. That's too immersive actually. But so this is work in progress actually. Then from an engineering point of view, on the left, you see a shimmy behavior. Yeah, sorry. Because our experience, the experience with simulators is that all the information should about be the same quality. So if, for instance, if you have a car simulator and you have a very coarse graphic representation, but the handling and everything feels like a real car and everything vibrates and so on, people are not happy, and vice versa. So all the information channels should have about the same. And in yeah, yes, yeah, 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 yes, correct. Yeah, yeah, yeah. Me too. Yeah. Yeah, yeah, totally the same. And I'll come to you in a sec. I want to connect to this. So there is a tendency, for instance, to make the virtual the projection of the world where you're in to make it far more realistic. We want more realism, more. I don't think that is always the way to go. Sometimes a Nintendo Wii approach, where you have an avatar which you see in a third person view there, riding a bike, would even be better than this almost very super realistic feedback. Because as you know from the Nintendo Wii, you quickly identify with that person. I mean, if you steer on the machine and that person is doing the same, or if you're doing the tennis and the avatar is doing that, you identify that's you, right? The same you can apply to these simulators. And that is a very novel thing which is going on at the moment. But I just want to put it in your head. There's the ethic. Yeah, augmented reality. Yeah, 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 yeah. But augmented reality is very nice. For instance, within elite cycling, we the project is not done yet. We have a project where we want to help riders to elite riders to descend. How should you descend? And nowadays, when you talk about elite cycling, how do they learn to descend? They say, "Who's the best? You're the best descender. Okay, follow that guy. Follow the guy." You're totally scared to follow that guy. So we had a whole program where we measured what is the best guy doing compared to the other ones, and then actually the next step was to project it with augmented reality on the road to show what is the ideal line which you should ride, where should you start braking, where should you continue riding, where should you start pedaling. That's still work in progress, but that's what they augmented. Yeah. You mean outside in the real world? Yeah, well, the thing is that we want to do experiments where we really put the people to the extreme such that they can fall. And then the ethical, and if we then need subjects, then the ethical committee says, no, no way. That's, yeah, or your head. Yeah, yeah. So, for instance, you want to investigate if an e-bike is safe under a certain condition, at a certain crossing. Is it a safe crossing for elderly on an e-bike? And then so you recruit a number of elderly, and then you have a dropout of say 20% of the elderly. They end up in the hospital. That's not really ethical, right? That doesn't work. So. And if you say please, still. Mhm. Um, where was I? Oh yeah, okay, the shimmy. Now I know. So and other projects are bicycle manufacturers. They experience in this step-through frame, this where female bike uh, with an electric bike, suddenly this shimmy behavior. So fast oscillation of the steering assembly, which has to do, of course, with the flexibility of the frame and the tires, etc. And we were able to make a design tool for the industry such that they can put in numbers and they can say, oh, is it sensitive to shimmy, yes or no? Why did it start at now and not why didn't they have a shimmy problem in the past? Well, for the elite cycling, they have the shimmy problem because they go very fast and it are light bikes. In the consumer market, well, people were not going so fast, 25 kilometers per hour, and it's an electric bike. Mass distribution is a bit different, and their hands are not so tight on the handlebars because they can relax pedal. They put in not so much power, so suddenly this time started to oscillate. Then on the right, you see this steer assist bike. We looked at tires. There was nothing known about bicycle tires in the term of cornering stiffness, camber stiffness, those kind of things, which are known in automotive world, but for bicycle tires. And we need that to make our models. The other one was that is a nice project, team time trial. So you had the individual time trial, but now some years ago the team time trial started in these races. So with let's say with 8 persons, you start, and the first 5, when the 5th one passes the finish line, that's your time. So you can drop off 3 if you want to. And then we thought, oh, this is cool. This is an optimization problem because you have motors, 8 individual motors. You have 8 individual resistance. One is larger than the other one, etc. And then you can schedule who's going at the head and for how long, and then he goes back to position 3, and then because people at the back have a different resistance depending on the people in front of them. So it's a whole complex schedule, but we love that. So we made a nice optimal simulation thing, optimal control thing with that, and then we came with the schedule. So it's pretty easy. Number 1 starts there for 6 seconds, then drops back to 3 and 2 for 12, and then drops back to 6, and we had it all worked out. And then they said, "We're not going to do that." I said, "Yeah, but this is the optimal." I said, "No, we're not going to do it." Why? We cannot control, we cannot direct them. There is no way how we can instruct them to do this. The only thing they have is one earpiece here in their ear, and they hear everything. They hear the coach, they hear the other riders, they hear everything. It's a hell of a noise. We cannot do that. So we have to make it simpler. So we put some more constraints, and then the idea was put a fixed time for every individual at the head, drop back to the tail, and then with that scheme we were able to improve because at one of the gyro elite cycling thing, I think it was a Team Alpecin or so, they did pretty well. Everybody thought, oh, hey, how could they perform so well? We didn't expect that. That was maybe also because of our optimal team time trial stuff. Yeah, and the descent, I talked about that. And the other one was a new bicycle for the track cycling team. And those are among a few projects we did within this bicycle dynamics and control. Sorry that I took so much time with you, but I think yes. Yeah. Yes. 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 Yeah. Yes. Yes. You have these closed wheels. Well, the thing is that the problem with resistance is about turbulence, creating not too much turbulence. And apparently, the disc wheels they create less turbulence than the spoke wheels. So it's all about CFDs. CFD calculation just proves, hey, with closed disc wheels, it's actually better. And there's not much maneuvering going around, right? If it's just straight ahead, disc wheels have less resistance. Yeah. Yeah. That is the idea I have. We haven't done real research on that, but that's my idea. And I hope in the future when we have a simulator which from a sensorial point works well with the leaning and the steering, and then we can try and change all these other channels, the vision, but also the vestibular. So there's a lot of discussion about this vestibular, and there's a big problem also with a bicycle simulator if you want to go around a curve because you are in equilibrium in the curve. How do we create it on the simulator? Then you have to sit upright, right? That's the only way. So we have to do a trick for going in a curve, like a transient, and then slowly back to up normal when you're in the curve. And is your vestibular really that important? Yes or no? So we have to do research where we stimulate it by uh, making it deaf, right? By putting electric stimulation there and see does it work, yes or no. So there's a lot of room for research there still. Yeah. Yeah, vestibular organ, yeah. Vestibular. Yeah. We want to study the human on the bike. That is the purpose. So, for instance, if I showed the Groningen simulator, we built that machine. We built this machine because the question was, traffic psychologists said, we want to assess the behavior of elderly in starting and stopping on the bike. But that is not the question Groningen wants to address. But we can talk later on that, maybe. Um, yeah, I saw a question there. At higher speeds, yeah, not necessarily. But let me rephrase it. Gyroscopic effect can help on the self stability. So, but it's not necessary for the self stability. That's actually the message I want to give. And then, if you want to know for a specific bike, what contribution helps, or then you just we have the model. You can change the numbers a little bit. There's even a MATLAB GUI interface where you can change the mass of the, or do crazy things like the wheel has a mass but no mass moment of inertia, and then you can study that effect of what is the effect of the individual parameters. But you have to be careful because, as I tried to explain, the self stability is a whole. Is these three things together? It's a gyroscopic effect, it's a mass distribution, it's about geometry. And you have so many, you have 27 parameters to change that. So you change this a little bit, and maybe you change that also a little bit. And so you have a lot of freedom, actually. That is the main message. Does it address your question? Yeah? Okay. Okay. I see one at the back. Good question. So now we make it even simpler. Not two wheels, we just take one wheel, right? Yeah. 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 Well, looks a lot like this, right? The one wheeler or mono wheeler looks a lot like this stick which you have to balance. So the whole idea about, oh, if I fall over, I have to move that contact point in that direction, still holds for the mono wheel. I mean, how else would you do it? Then remains the question is how do you steer on that thing? And that is by this relative rotation with your upper body with respect to that mono wheel thing. But you need some forward speed to do that, and that's exactly what you see in the mono wheel. But a funny thing with the mono wheel, so that we're talking now about lateral stability, but far more difficult is forward stability. It's more unstable in fore aft direction than in lateral one. So that is actually the first you have to try and control, that you're not falling over backwards or forwards while you're cycling. And then the lateral is a bit of secondary. Yeah. Yeah, you address a nice topic. Yeah, yeah, it's very intensive for you mean balance training. Yeah, yeah, yeah. So we are even thinking of a project in the future where people who had like some brain problem or had an attack, uh, they usually have trouble in balance and in walking. And then the rehabilitation is very complex because you need these two bars and you need two helpers to help them, or a harness with a robot. And we have the idea that a machine like that can help them regaining balance, and that balance is transferable to walking. So two steps in the research, but who knows? Because on this machine, you can, in a very safe way, you can train your balance because we can crank up the machine, make it very stable. And most of the people in the Netherlands, they know how to cycle, so they have sort of this balancing mechanism, and then they can train that on that machine. And gradually we make it more unstable, so they learn it, and then hopefully that's transferable to walking. But we don't know. That's research. Yeah. I have a question for you, for the audience. Can I? Yeah. In the beginning, I showed this bicycle which oscillated, and the oscillation died out. Became in the self-stable motion. I showed a model which was energy conservative. So apparently, in this, the energy in this lateral motion goes away. No, cannot go away because it's energy conservative. So if this lateral motion dies out, where does the energy go? In the Yeah, correct. So the bike goes a little bit faster. Yeah. And it's a little bit because the energy, of course, in the lateral motion is not so large compared to the forward motion. So it's a little bit increasing the forward speed. Very good. That's a way to propel. Yeah, you can propel. Yeah, correct. I even know a guy from standstill who can start cycling by this. Yeah. Okay, was my pleasure. Kiitos. June and August. July is holidays, right? So I'm away, but June and August I'm here. Yep. And my office is somewhere up there, top floor, 7th floor. Feel free to knock on my door.